Good morning, class. I hope you had a good weekend. So, what we will do today, the plan for today and Wednesday, in total, we have 4 more classes, including this one. In between these 4 classes, one will be test 4, and the very last one, which is lesson 42, we will go through the solution for test 3 and 4 because I didn't go through the test 3 solution. So that's what we will do on the very last class, and we will discuss about the finals, like what would be the question types and what I expect from you and everything. So that will be the very last class. So that leaves 2 classes today and the Wednesday. So the plan for these 2 classes is we will complete the class example 25 today. We are almost done. We just need to do one more trial and error for that one. And then we will start the very last topic of this course. What if we have more than one pipe? How can we incorporate all the head losses concept in pipe systems? Okay, so that's what we will do. But I don't think the multiple pipe systems will be included in your test 4. So I will tell you for sure on Wednesday, like what is the actual syllabus for test 4. But most probably it will be your dimensional analysis, whatever the similitude, and then 3 types of problems of pipe. That will be the syllabus for test 4. Yes. Yes, we will. No, it's not posted. I will do that. So open your class example 25. So since we started before the weekend, maybe all of you forgot everything about this one. So let's do a very quick review for class example 25. We had a cast iron pipe, which was used to transport water from the city municipality to the a certain residential area. We know the demand of that residential area, which was 10 feet cube per second. We also know the head loss or the system loss, energy loss within the system per unit length of the pipe. Now, as an engineer, it's your task to find what will be the pipe size which can carry this amount of water, like 10 feet cube per second water within its size. So that's what we were trying to do. We know the head loss, but we don't know all the friction factors and everything. So we will start from this point. Since I don't have the setup for the full system, like starting point and ending point, so energy equation is not helpful here because I don't know what was the pressure, what was the velocity at starting point and the ending point. So what we did, since we know the head loss equation, we started from, and the head loss magnitude, we started from that point. They also told us to ignore the minor losses. So I'm not doing anything about the minor losses. I'm considering all the loss happening here due to the friction. Okay, so that's what we did here, like F1 over D V square over 2G. Now, friction factor is not given here because friction factor itself is a very complex thing. It depends on flow type. It depends on what are the pipe roughness and everything. It can be new pipe. It can be old pipe. So friction factor is like you need to calculate for that specific type of like scenario. So that's what we will do here. So we started working from this equation. We ended up here. And since we are looking for the diameter, we set our equation in such a way that diameter equals to something because we want to know the diameter. Now you can see here, the friction factor is unknown. Now, if you can review a little bit, for finding friction factor, we need to know the Reynolds number. For Reynolds number, diameter is important, which we don't know. So again, we are in kind of limbo that we need the friction factor to determine the diameter. At the same time, we need to know the diameter to determine the friction factor. Again, it's one equation, 2 unknowns we can't work with, right? So for this type of situation, now we are a little bit experienced. We know how to work on that. when we don't know something, what we will do, we will assume something and we will try to justify our assumption. If our assumption is correct, we are fine. If not, we will do a different assumption, right? So that's what we will do. We will assume a value for F, but for doing that, we know the friction factor is different for laminar and turbulent flow. So our very first step is we need to know the flow type, whether the flow is laminar or turbulent. So calculating the Reynolds number, like using the Reynolds number, we can identify whether the flow is laminar or turbulent. So that's what we tried to do. But again, we had the same problem that we didn't know the diameter. So we stopped at that point. Now we will start from this point, that how can we solve this problem, that so that we can find the friction factor and then we can find the diameter. Okay. Okay. So as we already know, we will assume the friction factor F. So that's what we will do here. Now, when we will start the water resource engineering course in your next semester, you will see we use a different, like there are some other options also. So we usually use another equation for pipe distribution called Hazen-Williams, and you will love that equation because there is no trial and error. But that's for the next course. Here we have to deal with this one. So what we will do, since our final objective is to get F from Modi's diagram, okay, and to get that we need epsilon over D, and we need the Reynolds number. And if you look at here, for Reynolds number, we need to know the D. So that is D. And if we go back again, for finding D, we need to know the friction factor. So that will be the assumed friction factor here. Okay. So make sure you have enough space because you need to calculate the percent of like percentage of difference and everything. And what I will do now, I will write down all the expression. So for D, the expression was 419.6 F. 419.6 F to the power 1 over 5. For Reynolds number, 1.01 10 to the power 6. 1.01 10 to the power 6 over D. Epsilon over D is, we know the epsilon. Did we find the epsilon or not? Okay, we didn't find the epsilon. So epsilon, what is the pipe material here for classic cast iron? Okay, so for the cast iron, this is the epsilon. Make sure you count the zero properly. There are 3 zeros. So 0.00085 feet. Okay. Now, as I said in previous class, F equals to 0.02 is a very first good estimation, but you can assume any initial value. There is no specific rule or anything, but usually this one gives within maximum 3 trial, you usually will get the result here. Okay, so for friction factor F equals to 0.02, what will be the diameter, what will be the Reynolds number, and what will be the epsilon over D? Give me that numbers. What number will be that? $1.53. Okay. What about the Reynolds number? Six 6.69 10 to the power fifth. Okay. And the epsilon, give me the epsilon over d in terms of decimal number. Okay. And make sure there are 3 zeros, because we had some problem in section 1 because of these zeros.
6.6 10 to the 5.
Okay, give me in this way. 0, 0. What is epsilon over d? Okay, 0, 0, 0, 5, 6. Okay, why don't we just round it at 6, because that will help us to find the line in the Moody's diagram. Now, we are ready to use the Moody's diagram because we have one set of Reynolds number and epsilon over d. If anyone needs Moody's diagram, I have some extra if you forgot your one. So what we will do, we will go to here, and our first task is to find 0.0006 line, like for epsilon over d, right? So let's check if we have one. We already have 0.0006 line, which is good. You don't need to draw a new line. So just highlight that one, 0.0006 line, that one, okay? Here, that one, highlight that one. And the next step is you will draw a vertical line for Reynolds number, right? So the Reynolds number was 6.65, 10 to the power 5. As I said, always find the 10 to the power like 4, 5, 3, that line, and go on the right direction. Okay, not the wrong direction, right direction. So 10 to the power 5, and then 6.65 will be in between this point, that one. Now, after that, you know how to find the friction factor. What is the next step after that? Just draw a horizontal line and move to the left. Now, you may get a little bit different from 0.018. That is absolutely fine. But you should get pretty close to 0.108 because you didn't draw the 0006 line. This line was there. So there is a very small chance to get something else other than 0.018. Okay. So find that, whatever you got, use that one on the table and find the percentage of difference between the assumption and the one you got from this diagram. Okay. How many of you got something close to 0.018? Okay. Okay. I will wait 1 minute. Those who already got the friction factor value, what you can do here, find the percentage of difference. 0.018 minus 0.02 divide by 0.018 multiplied with 100. 11%. Oh, almost there. But we want to get this value close to 5 or less than 5, right? So we have to do one more trial. Now for the second trial, you can use any other friction factor values, but it is wiser if you use this value. Again, that will, yes. No, we are, because we are trying to find what is the how much, like how much difference was our assumption was. That's why with respect to the value from the Moody's diagram, how much different the assumption was, that's what we are trying to do. So we will not divide by the average. We never. I don't think there is any, like, you can use the average value to find the percentage of error if you have like hundreds of when you use that statistical application, you find like you have hundreds different numbers and you always find the summation of percentage of difference with respect to average. Usually we do that for rainfall calculation or something, but here, since we have only one value, we don't need to find the percent of. Usually it depends on like what type of application you are trying to do. Here our main objective is to find how much difference or how much what is the difference in our assumption with respect to the Moody's diagram, because we want them to be same. That is our main goal. Like our assumption should be same as the Moody's diagram F value. That is our main objective. And that's why we try to find, if it's not same, what is the difference here. And that's why with respect to that value, like here, we are trying to find the percent of difference here. Okay. So you can use average, but not here. That will be something else. Like there are some other applications where you can use the average of these two or something like that, but not here. Usually mean, median, there we usually use the average. Okay. Okay. So anyone did the second trial? Okay. So do the second trial. What did you say? That should be, yes. So, okay, I will wait 1 minute and make sure everyone has the second F value. Just let me know. Okay. I want to make sure you all know. Diagram. You got what point? That's what I got. So that is basically 0%. Now let's got the second friction factor. Oh, that's pretty close to 0.08. Right, so that is 0% error for your case. So that's why this is just number. It just that's the only difference. Yes. Or are you going to go? Okay, that's one. Just to press it. Yeah. That can be because of that is okay. That's just fine. Something. You are going to say. 0.16. Which is weird. Yeah, actually, I think you just find the correct Reynolds number most of it. And because the error should decrease. Okay, class. So some of you got 0.01. Okay, before that, give me the D value for this F. 1.5. Okay, what is the Reynolds number? 6.74 10 to the power 5. And what is the epsilon of? Oh, this time epsilon over D will be changed a little bit. But I think if we round that, that will be again 6, right? It was 0.00057. Okay, so some of you got 0.016, 0.017. I got 0.018. So I'm using that one. But if you get something else like 0.017, 0.016, check that again. For the second time, if you still get that, keep that and find the percent of error. And if it's more than 5%, just do one more trial. Okay, so usually the percentage should be decreased. Like initially we had 11, the next one should be 8, 7, 5, something like that. If it is increased, there is a high chance that most probably the calculation was not correct. So check that. Okay, so for this one, since I got 0.018, 0.018, I got 0%, which is great. But if you got something else like 1, 2, 3, 4, 5%, that's fine. Okay, now it seems some of you are still struggling with the Moody's diagram. Okay, but in last class, I think all of you could get the correct friction factor. So just want to remind you, please make sure you know how to use the Moody's diagram. The test 4 is the one usually people catch up most of the time, because test 4 is one of the easiest tests you will have after test one. I know test one you did really well because that was till now that was the easiest one. Test two and test three, some of you struggle. Usually test four people usually catch up because we don't have big syllabus. It's just 3 different types of pipe problems and dimensional analysis and everything. So those who are struggling between D and F, and anyone who wants to improve your grade, please take the chance of test 4. And for test 4, to know how to use the Moody's diagram is very, very important. So please make sure you know that. If you still struggle, I'm here, ask me. I'll be happy to explain it times how to use the Moody's diagram, okay? So are we good up to this point? Okay, so what we will do, since I got 0.018, 0.018, basically the diameter I will get is 1.5 feet, right? So if you got something else, just calculate the new here. The friction diameter was, what was the 419.6. 1/5. So 419.6, 0.018, 1/5, which is 1.5 feet. And if you multiply this by 12, that will be what? 18 inches, right? Now, for my actual calculation, I got 17.98 inches. That's okay. Here we got correct 18 inches. Section 1, they got 18.2 inches. Now, the reason I'm discussing that, we always choose the next higher diameter. So suppose we got 18, which is good. 18 is a good number, but for some reason you got 16.2 inches. You can't order 16.2 inches unless you set up a company, your own company, which will produce 16.2, but you will be bankrupt soon because no one will buy that pipe. So what we will do, we need to check what are the commercially available pipe size we can have. And this is the list for cast iron. So here you can see we already have 18. So that's good. We don't need to choose anything else. For some reason you got, if you got 16.9 or 2, which pipe you choose here? 18. For some reason you got 18.7. Which pipe you choose here? 20. That's because we need to make sure the pipe can carry 10 feet per cube, 10 feet cube per second water. If we choose less than our design, like the one we got, that means that pipe will not be able to carry the full water. That's why we will always choose the pipe, the next big size, okay? So for our case, 18 inches, it was sheer coincidence that we got exact 18 inches, but for any reason we got something else. That's how we needed to choose, okay? And that's what you will see for your homework 11. Now you are ready for your homework 11. For your homework 11, there are 3 problems, one for pressure drop, one for velocity, one for diameter, and we are done with the diameter one. So now you are fully ready to do the classic homework 11, okay? Okay, now up to this point, are we good, everyone? You're nodding your head, but when I go to individual person, you're struggling with the friction factor F. So tell me the truth. Are you good up to this point? Yes.
So what are we using? Like, on our homework, this is like we use a table sometimes to find the frictional factor. Sometimes we just use the energy equation. Is that like the area equation?
The energy equation we usually use if we have the full setup, like we know the starting point where we know the pressure, diameter, pressure, velocity, everything, and the ending point, pressure, velocity, everything. But here we only know the details for 1 feet of pipe. I don't know what was the initial point. Was there a reservoir or anything? So if we go back to our class example, the very first class example, like this one, here I knew we had to calculate the pressure at A, and I knew it was open to atmosphere or something like that. So I kind of knew the pressure and velocity at the starting point. and the ending point. That's why I started from the energy equation. But for class example 24 and 25, I don't know anything. They just gave me the total head loss per unit length of pipe or something like that. So even if I want to apply the energy equation, there is no way, because I don't know what is the pressure at starting point or what is the velocity at starting point. So that's why I started from this point. And that is a very good question. And I get that question. I got that question a lot during tests, like how can I use the energy equation or something. So that is the answer. If you know the total setup, whether it was open to atmosphere or not, whether it was a big reservoir or not, that means if you know the pressure and velocity and the elevation at starting point and the end point, you can apply the energy equation. If not, you will just start from this point. Okay, does that answer your question?
Yeah.
Okay, yes.
Are we going to be able to use like now on the test?
Most probably no, but the way your homework is set up, like with splitting question in your test, you will kind of have the kind of same setup. So you will kind of know like after which step what you need to do. Okay. Okay. Anything else up to this point? Hi. The pi number means like how many pi numbers you will have, something like that, or either I can give, either I will give you, or I will set the questions like that way. What is the total n? What is the m? And you know, number of pi is n minus m. So you will just subtract from, you will subtract the m from n. Okay. Okay. Anything else about up to this point? Okay, if not, we can start the very last topic of this class, which is if we have more than one pipe, how can we incorporate all the concepts of head loss? Okay. And if we have more than one pipe, like we already deal with more than one pipe, but everything was same diameter. Now, if we have different diameter pipe in one system, how to work on that? That's what we will do. And that is actually this class handout. Okay, the one I just gave you today. So let's work with this one. We have kind of 15 minutes. So what we will do, we will try to understand different types of pipe system we can have, and we'll try to understand the hydraulics. If we have time, we'll start class example 26. If we don't have time, that's perfectly okay. And there is a high chance that these will not be included in your test 4. Okay. Okay. As I was saying, if we have multiple pipes with different diameter, we can have different types of arrangement. And in this course, we will only focus on 2 common types. One is pipes in series and pipes in parallel. There can be other setup also, but we will cover those in your water resource engineering, not here. So pipes in series, from the name series, you know, series means something added in serially, right? One after another, one after another. It's kind of like relay. Do you know the relay run? Like one person ran up to that point, he supplies something to the other. So pipes in series is exactly same thing. It's like one after another. What flow will go from this point to this point, this point to this point, this point to this point. It's like kind of relay run, like something is transferring from one point to another point. That is called pipes in series. And we see this type of setup like every time we have a larger pipe or something like that. For pipes in parallel, parallel means all the pipes, they have the same start point or starting point, and they will end at the same point. Okay, So their starting points and ending points are same. That is the parallel pipe system here. Okay. And as I said, there can be different types of other system also, which is not series, not parallel, but we are not discussing those in this course. We will do that in water resource engineering. Okay. Now, since we will mainly focus on these two types of pipe system. We need to know what are the hydraulics here. So that's what we will try to discuss. And you will see, you already know these stuffs. It just we will identify these hydraulics. Okay. Now here, this is a pipes in series. We have three different pipes of three different diameter. That is the Q in, and that is the Q out. There is no other outlet or inlet. And within this pipe, flow is Q1. This one is Q2. This one is Q3. Now, do you think Q1, Q2, Q3, they will be different or they will be same? Q will be same, right? Because there is no other inlet, outlet, nothing. So what will be different? Velocity, because of the different area, right? Good. So that means we will have Q in equals to Q1, Q2, Q3, Q out. Okay. So that is one thing. Now, what about the head loss? For pipe 1, we will have head loss 1. For pipe 2, we are having head loss 3. For pipe 3, we are having head loss. So if I want to calculate the head loss from point A to B, what do you think? What will be the total head loss? We need to add or we need to multiply the head loss one by other, or like what will be the head loss in total? We will add that because the larger the pipe size, the larger the friction and everything, basically we are adding those. So that is our second principle. For this head loss, we will use head loss 1, head loss 2, head loss 3. And what is head loss 1? That is head loss 1. That is head loss 2. That is head loss 3. And each head loss, it will be major, minor, major, minor, major, minor. If we don't have any minor losses, that is fine. If we have something for individual, like point 1, pipe 1, pipe 2, pipe 3, we need to calculate those. Okay. So that one was easy. We kind of, you already understand this part. Now the next one, pipes in series. Here, oh, before I go to the pipes in series, for each pipe, since the velocity is different, the diameter is different, the friction factor and Reynolds number for each pipe will be different also. And that is the clumsy part. It's like it will take more time if we don't know the friction factor. Okay. Other than that, all the calculation steps are same. Now pipes in parallel here, again the Q in and Q out. This one is Q1, Q2. Now what will be the relation between Q in with Q1 and Q2? Flow is going through this way. So what will be? It will be half. It will, yes, that is the correct answer. I think if you say that it will be divided into two parts, that will be the correct answer because I don't know the diameter and the velocity. So these will be the correct thing. 1 plus 2 If the pipe diameter, length, friction factor, everything is same, it will be divided into 2. If it's not, we need to calculate how, like what are the percentage going into each pipe, but that is the one. Now, if I had 100 pipes here, it would be Q1 plus Q2 plus Q3, Q4, like that way, right? Okay. Now, for the head loss part, it's little bit, it's we need to understand a thing before we discuss the head loss part. Now, before doing that, all of this pipe, that is their starting point, right? And that is their end point. Now, if you can remember, we can connect the head loss with pressure drop, because pressure drop is the like indication of the head loss, and we can connect that. Now, for pipe 1, what is the pressure drop? Pressure at PA minus PB, right? That is the pressure drop for pipe 1. Do you agree on that? What about pipe 2? What is the pressure drop? This is the starting point and this is the end point. So what is the pressure drop for pipe 2 also? The same thing. If I added hundreds other pipes in between A and B, their pressure drop will be what? Same. That simply tells you when pipes are connected in parallel, the head loss inside each pipe is actually same, because it is connected between 2 points, and head loss is always like it happens between 2 points. Okay, that simply tells you the head loss 1 equals to head loss 2, major, minor, major, minor. Okay. Now you can see for each type of system, we have 2 individual equations for Q and head loss. In addition to that, we have energy equation, we have continuity equation. So as long as we can identify the types of pipe system, it's not that much difficult to work on that. Okay. Up to this point, if I ask you to differentiate between pipes in series and parallel, you'll be able to do that. Like you got the idea which one is. If I say, okay, if I give you one picture and ask you what type of pipe setup is that, it's a pipe in series or parallel or nothing, you can identify that, right? Good. Okay, yeah, so that's what I had for the theory. We still have 6 minutes. Why don't we start working on class example 26? Maybe we'll be able to just identify the given values and sources of minor losses, and we'll start from that point on Wednesday. Okay. So who will read the class example 26? The question statement itself is a big one, so it will take time to read that. Mm-hmm. Okay, thank you very much. So basically, the question statement is very large because they explain everything about minor loss sources and everything. In easy word, they are asking you to find what is the flow inside this system. Okay, that's what they are asking. Now, You already did this type of problems. You have a reservoir, you have a pipe, you need to find the flow inside the pipe. The only difference here this time, we have two pipes with two different diameters. Okay, pipe BD, which is pipe 1. I will name that as pipe 1. And we have pipe DE, which is pipe 2. And for each pipe, there are some minor loss sources. There are two cases. Case 1, we already know the friction factor. For case 2, we don't know the friction factor. So that will be a little bit difficult, but we will work with the first case first, where we know the friction factor. Okay. So what I will do, I will just write down all the given values first, and then we will proceed. Okay. So I named the pipe BD as pipe 1 so that I don't have to write BD every time. So the very first given values are the diameter, right? Which is D1 is 6 inches and D2 is 3 inches, right? Now we know the friction factor F1 0.021, F2 is 0.024. We also, they also give us the minor losses coefficient or sources. So in between B and D or pipe 1, what are the minor losses sources? What is the obvious one you can see in between B and D, which can create a minor loss? Which is the obvious one here? Any irregularities, any obstruction on the flow. The pipe is not straight, right? BD. So that is the very first source, which is the elbow here. And there is one thing called flash entrance. Flash entrance means when the water is entering from a big reservoir into a small pipe here. The huge amount of water is entering into a small diameter pipe. So that will create a head loss. So that is another source here. So in total for pipe 1, we have summation of KL1 equals to 1.4. And for pipe 2, we have one valve here, which is fully open gate valve. And there is a filter C. So in total, the coefficient is 0.89. Now, some of you may ask one question that, ma'am, the filter is on pipe 1. Why we are considering that for pipe 2? That's because when the water will go enter from pipe 1 to 2 through this filter, it will actually affect the flow inside the pipe 2. That's why we are considering that as a part of pipe 2. Okay. And so we have KL1, KL2. These are the sources here, right? And what we need to calculate finally for this one? The flow Q, right? Okay, those are the given values for QE. And we know what we need to find. Can you tell me what type of pipe system is it? It is series or parallel? It's series, right? Okay, great. So we have two equations for Pipes-in series. We will use that. I will start that from this point on Wednesday, okay? Make sure you work on your homework 11 that is due today at midnight. Thank you, class. I'll see you on Wednesday.